Today's topic is a one-way light path. You may not have heard about this. Anyway, let's experiment with two pieces of transparent film and a polarizer filter. We affix the film to the first polarizer filter, like so. On the second filter, we turn the film 45 degrees before affixing it. There is practically no difference when we hold them up to the light. However, when we put them on a metal plate, look, the one on the right is darker. This means that less light is getting through the filter on the right. There are two possible explanations for this. First is that the light isn't able to pass through the filter from the source and reach the metal plate. The second is that the light from the source passes through the filter and is intercepted by the filter after being reflected by the metal plate. Which is correct? Let's confirm this with a laser pointer. We place a mirror and one of the filters like so, and shoot the mirror with the laser through the filter. Light is reflected by the mirror onto a small piece of paper next to the laser. From now on, we'll call the filters normal and 45 degree to indicate their respective orientations. First, let's try the normal filter. We can see the reflected laser beam on the paper. Next, the 45 degree filter. Oh, the beam has weakened substantially. It is quite obvious that this behavior is related to the difference in darkness seen on the metal plate. Where is the light being intercepted? To investigate this further, liquid nitrogen will be useful. We're using it not for its cooling properties, but rather because the vapor it emits enables us to see the path of the laser beam. First, the normal filter. The beam reaches the paper via a V-shaped pathway. What about the 45 degree filter? The beam is interrupted at the filter after being reflected by the mirror. This side of the filter is blocking the laser beam. Well, wait a moment. The other side of the filter doesn't block the beam from the laser pointer to the mirror. In fact, this filter acts as a one-way light path. It's called an optical isolator. Although you may never have heard the term, this device plays a very important role in our daily lives. For example, a laser welder. The light it emits is so strong that it can melt metals. If this light were reflected back onto the welder, it would be destroyed. Thus, every laser welder has an isolator to prevent this. It is also important in telecommunication systems. Light signals are partially reflected by the connecting surfaces of optical fibers. An optical isolator is mounted at the output port of the light source as a safety measure. These materials' unique properties play important roles, don't they? Now comes the tough part for those who are interested. Here is a simplified explanation why this filter acts as a one-way light path. Only laser light that is parallel to the direction of the polarizer filter propagates through it. This is called linear polarization. After that, the light oscillation direction is twisted by 45 degrees by the transparent film. This light is propagated as a spiral. This light is then reflected by the metal surface, reversing its oscillation direction. It is then twisted again by the transparent film, converting it into linearly polarized light. Consequently, the light arrives at the polarizer filter perpendicular to the polarizer's orientation. That's why the reflected light is blocked there. Is this difficult to understand? Watch it again carefully and try to get a sense of what's going on.